Start recording. And I will start this up. Okay. So this is chapter 11. It is simple linear regression. So this chapter is probably the most useful to real life that I have found. You can use regression for classification, prediction, forecasting, etc. We will talk about it today at a rather low level, but it is vastly useful in business and especially in the tech industry. So the goal of today is to learn about simple linear regression, also called SLR. You recall from high school algebra of a line is y equals mx plus b. That is the formula for a line, and today we are going to talk about how to fit a line or a linear model to a set of data. We're going to introduce the straight line simple linear regression model as a means of relating one quantitative variable to another quantitative variable. We'll assess how well the simple linear regression model fits the sample data, and we will introduce the correlation coefficient as a means of relating one quantitative variable to another quantitative variable, and employ the simple linear regression model for predicting a value of one variable from a specified value another variable. So first, we're going to talk about models. In particular, mathematical models. We want to describe the relationship between the variables where x is an independent variable and y is a dependent variable. Our model will try to explain a phenomenon that is going on in our data. There are two types of mathematical models, deterministic and probabilistic. A deterministic model hypothesizes an exact relationship and are useful when our prediction error will not have any major negative effects if we are wrong. So this example here is that force equals mass times acceleration. So notice that there is no error term in this model. So when we look at the next slide, look for the error term. Probabilistic models, on the other hand, are interested in that error term. So there are many probabilistic models, and we are interested in that random error that's sometimes is represented by lowercase epsilon, in this case, and other times it's represented by a lowercase. So here we have an example where we want to predict sales volume based on the amount of advertising spending. So it states that we will increase sales volume by 10 times the amount we spend on our advertising plus or minus some random error. So here is the general form of a probabilistic model. We have our y dependent variable is equal to a x independent variable plus some random error. So our model in standard form is y equals beta 0, which is the y-intercept, plus beta 1, the coefficient of our x term, plus some random error. So y is our dependent or response variable, and it's the variable to be modeled. It's what we're trying to predict. The x variables are independent or predictor variables, and it's the variables we're using to try to predict that y variable. We're looking at the expectation of y based on beta 0 plus x. and then E, or this epsilon, which is the Greek letter epsilon, counts for the random error component. And ideally, in our model, we want to be able to explain as much of this random error away, and thus minimizing this, or getting the lowest epsilon value that we can. So probably the most important part of the function is the interpretation of the beta 1 coefficient. So we're going to be very interested in this coefficient. Very rarely will the beta 0 intercept have any real-world interpretation. Sometimes in some economic problems it does, but most of the models that I work with do not have a real-world interpretation for the beta 0. However, the beta 1 coefficient is the slope of the line we are estimating, and can be interpreted as an increase in 1 for every 1 unit increase in x. So this kind of visualizes that model. Y-intercept over here shifts up and down the line, and but the beta 1 value changes our estimated line. So this slope will change kind of the pitch or slope of the line. So beta 1 is the more important that we learn to interpret. So we will use a 5-step process for simple linear regression. First, we will hypothesize the deterministic component of the model that relates the mean or expectation of y to the independent variable x. Then we use the sample data, unknown parameters in the model. We specify probability distribution of the random error term and estimate the standard deviation of the distribution. Statistically, we evaluate the usefulness of the model, and then when satisfied with that model, we use estimation or some other purpose. So now let's talk about actually fitting the model. We will use something called ordinary least squares approach, or OLS. Let's say we have some data that we plot on a scatter plot. Our goal will be to fit the line, or find the line that fits the data the best. This data looks relatively linear, so I think it should fit. But what line actually? So how would you draw a line through all the points? And how do you determine which line actually has the best fit? So we're going to a line that has the least squared distance from each point to the line. Why is it squared? Well, because are above the line and some points are below the line. So we have positive and negative values that would each other out. And by squaring all those values, it keeps them all positive, and we can maintain the true value. So the least squares line is one that follows these. The sum of the errors equals 0, or the conditional mean error is equal to 0. We're talking about the error term. So what this is, we're estimating a line, right? And we are not assuming our estimate to be wrong, because why would we go about estimating something if we thought it was going to be wrong, right? So we are assuming there is no error in our model. Hence, why it is one of the least squared assumptions. The second is that the sum of squared errors is smaller than for any other straight line model. So, for example, the error variance is minimized. So our whole goal is to minimize the error of fitting our line to our data on our scatter plot. So the formula presented here is how we find the different components based on the sum of squares. So we're talking about that distance from the point to the line, and we're going to square those. So first we have the sum of squares xy, and the sum of squares xx. So our estimated slope, beta 1 hat, so because it's an estimate, we put the little hat on it, is found by the change in the sum of squares of x and y by the sum of squares in the x term. The y-intercept, or beta 0 hat, is found on our average y value, y bar, and subtracting our estimated slope, beta 1 hat, times the average x value, x bar. So to find the sum of squares xy, we need to find the sum of the difference in the x values from the mean x value times the difference between the y values from their mean y value. So we take the sum of each of our x from their average, and we multiply that by each y subtracted from the average y value. And that will give us the sum of squares xy. The sum of squares for xx is the difference of each x from the mean of x squared. With these values, we can calculate out all of our beta coefficients. Finally, n represents the sample size that we use for our estimation. So we can find these in our data, and then we plug it into this formula to get our slope, and this one to get our y-intercept. For regression, you'll generally want a sample size of at least 30, but the higher the regression or the higher the sample size, the better your model will fit. So beta 0 represents the predicted value of y when x equals 0. So caution, this value will not be meaningful if the value x equals 0 is nonsensical or outside the range of the sample data, which, like I said, will be most of the time. Beta 1 represents the increase or decrease in y for every 1 unit increase in x. This interpretation is valid only for x values within range of the sample data. So what that's saying is when we create this model, we can only use this interpretation for within sample values. So if our highest or if our lowest value is like 100 and the highest is 1,000, once we go beyond 1,000, we're no longer in sample, and we have to change a little bit for prediction outside of the sample. So I think this visualization does a good job of explaining what is going on in linear regression. Each epsilon represents the distance and error from our estimated line, and obviously the best line will be the one that minimizes that distance. So we have our scatter plot data in the purple dots. We fit this line, and then this error distance, how far this line is from each of those points. We're trying to make that value for each of these as small as possible. Okay, so let's do a simple example, and I'll show you something in Excel, or a couple of things. So let's say you are a marketing analyst for Hasbro Toys. You gather the following data. You have ad expenditure in hundreds of dollars and sales units. And our goal is to find the least squares line relating sales and advertising. So in Excel, we have our ad expenditure, and our sales. So we have 100, 200, 300, 400, 500. And we have 1, 1, 2, 2, 4. All right, so there's a couple of ways we could go about doing this. We could insert a chart, say a scatter plot. So we have a scatter plot, that's what our data looks like. We can go insert a trend line. And let's see what options. Should be able to see display equation on chart. So that represents a linear regression, which is what a trend line is for this data. And that's a simple way to do it if you are only interested in this function. However, there's a lot more data that goes into a regression. So the other thing we can do is on the data tab in data analysis, we can go to regression, and then our Y value, what we're trying to predict is the number of sales, right? And we want to use that based on how much money we spend on advertising. Let's see, add line fit plots in so you can see how it generates the scatter plot. Now we'll put the data here. So we put labels. It'll generate a confidence interval anyways. I don't know if we'll get into probability plots right now, but you can see it generates a scatter plot just like we did inserting. Put the trend line in, put it over there, and see if it'll give us about the same. Gives us, oh man, same scatter plot with our prediction line. You'll notice that from that trend line that we created, the coefficient is the same and the intercept is the same. So if we get just this regression output, we would end up with, y equals 0.7. That is our beta 1 coefficient, x, and then it's going to be minus 0.1, because that is our y-intercept. So this is our beta 0. This will be our beta 1. So pretty easy to generate in regression. You'll see that it also generates an ANOVA because the ANOVA and regression are very closely correlated. You'll see that the ANOVA model, the significance f, is the same in this instance because it's simple linear regression as the p-value for our beta 1. So the scatter plot we generated. Let's see. This provides the manual way you would go about doing it. I highly suggest you use Excel instead of calculating out each SS or sum of squares, but this is how you would go about doing that for each of those points. It'll give you the same answer though. So our estimated line, linear function, is negative 0.1 for beta 0 and 0.7x for beta. So that's what our line looks like. So there are several assumptions that we need to go over before you can run a linear regression model. So let's talk about those. Assumption 1 is the mean of the probability distribution of epsilon is 0. That is, the average of the values of epsilon over an infinitely long series of experiments is 0 for each setting of the independent variable x. This assumption implies that the mean value of y, or the expectation of y, for a given value of x is the expectation of y equals beta 0 plus beta 1x. And basically, we do not expect errors, else why would we run the analysis in the first place? So just kind of boil that down. Assumption 2, the variance of the probability distribution of epsilon is constant for all settings of the independent variable x. For our straight line model, this assumption means that the variance of epsilon is equal to a constant, say sigma squared, for all values of x. Assumption 3, probability distribution of epsilon is normally distributed. That's kind of a key to the underlying reason all of statistics works. And assumption 4, the values of epsilon are associated with any two observed values of y are independent. That is, the value of epsilon associated with one value of y has no effect on the values of epsilon associated with another value of y. So another way to say this is IID. I don't know if you've heard that term before, but that means it is identically and independently distributed. So you can see how the error terms distribution is approximately normally distributed. So if you kind of turn your head sideways, you can see that's a normal distribution, normally distributed about our estimate. And that roughly we have the same error above and below the line. So approximately half of our data will be above the line, half of our error will be above the line, and half of our error will be below the line. So that kind of covers the assumptions. So similarly to the hypothesis test we were doing about the mean, we can use regression to do hypothesis testing. And both a one-tailed and a two-tailed test, our null hypotheses are that the beta 1 slope is 0. So what we're trying to test is whether or not there's any correlation between x and y, right? So if the slope is 0, that means it's not correlated. So this basically means that the coefficient for that x term is uncorrelated to the y variable. The alternative hypothesis for one-tailed is directional, which, like I said, very rarely do we come across times to use directional. And it's two-tailed if u is not equal to 0. So to get our test statistic, we divide the coefficient by its standard error. The absolute value of our t-statistic is greater than our rejection criteria, and we can reject the null hypothesis. Fortunately, Excel can do all of this for us. So almost all statistical computer software packages report a two-tailed p-value for each of the parameters, like I said, because most of the time that's what we're going to actually use. For example, in simple linear regression, the p-value for the two-tailed test h not equals 0 versus the alternative that beta 1 equals or does not equal 0 is given on the printout. If you want to conduct a one-tailed test of hypothesis, you will need to adjust that p-value reported on the printout as follows. So to adjust to make a one-tailed, we have to divide the p-value by 2, and depending on the direction, we have to subtract from 1. So if we have beta 1 is greater than 0, then we just divide that p-value by 2. And if we want to look at the other side, we have to take 1 minus that value to get the other side. Likewise, if we're looking at the lower tail, then it's going to be the same idea. So as long as the inequalities are facing the same, all we have to do is divide that two-tailed one by 2 to get the one-tailed. And if we want the other side, like the right side of the right-sided area, then we subtract 1 minus that value. So where does this p-value come from? We go back to Excel. You'll see our coefficient here, our standard errors here, and we just said that this t-statistic is calculated out by dividing the coefficient by the standard error. That gives us our t-statistic. Then it goes and looks up in the t-table to give us our p-value, but that is a two-sided test. So depending on our hypothesis, we would divide this value by 2 to get the one-tailed. You remember back when we were talking about the reason we use two-tailed more often is the p-value will be higher, so our estimate or our model will have to be better. Because if we let's say it was two-tailed was 0.1, well, now you divide that by 2, so we split that area in half, and now it's 0.05, and all of a sudden in a two-tailed version we would fail to reject the hypothesis. However, in the one-tailed version we could reject the hypothesis. So that's why you'll generally get a lot of scrutiny, especially in research, if you try to use a one-tailed test. Okay. 30. Okay, so to adjust, 30. Okay, so we can create confidence intervals for our coefficients as well. We add and subtract our t alpha 2 values times the standard error, and of course Excel generates that for us as well. So the 95% is given. I don't know why it always doubles that. If you go into here and you want to change it, you can hit confidence level and it'll give you the 90 instead, or if you want the 99, depending on what it is you're looking for. So you can do an example. So you are a marketing analyst for Hasbro toys. You find that beta 0 equals 0.1, beta 1 equals 0.7, and S equals 0.6055. And then you need to determine, is this relationship significant at the 0.05 level of significance? So you can go back to our Excel spreadsheet. That's why I calculated it out this way. So is it statistically significant? Our p-value is 0.03. And thus 0.03 is less than 0.05. So our beta 1 is statistically significant, and we can use it. The overall model is, in a simple linear regression, is that same value. However, our intercept is not statistically significant, so we would not be able to interpret that anyways. Okay, so let's see the way the test of slope coefficient works. So beta 1 equals 0 is the null hypothesis. And our alternative hypothesis is that beta 1 does not equal 0. So we use an alpha significance level of 0.05, which is equivalent to 95% confidence. Our degrees of freedom are n equals 5 because we had 5 samples. We are estimating 2 parameters, so 5 minus 2 gives us 3 degrees of freedom. For a two-tailed test, we look up our critical value, or our critical value is going to be plus or minus 3.182, and we can pull this from our Excel regression output to get the answer. Basically, we're splitting this value up into two tails, and our rejection region is above or below that number. So if we get a t value greater than 3.182, we can reject the null hypothesis. and our t-value was 3.657, which is higher than that number, and thus we can reject at alpha equals 0.05. Like I said, our Excel will give you the output here, and that's really just this number divided by this number gives you that number. So that's basically what this slide says. Our t-value is calculated by dividing the coefficient by the standard error, and we get 3.657, which is greater than our critical value, 3.182. So we can reject the null hypothesis. You can also look at the p-value, 0.035, which is less than 0.05, which also tells us to reject the null hypothesis. So remember, when we're talking about t critical values, higher is better. We're talking about p-values, lower is better. Okay, so now let's talk about the coefficient of determination and correlation in general. So correlation answers the question of how strong is the linear relationship between two variables. Correlation is determined by or denoted by the lowercase r if based on a sample, and as the Greek letter rho, which kind of looks like a P, for a population. To calculate r, we need to divide the sum of squares for xy divided by the square root of the sum of squares for each of the variables. So we find that by taking each x value from its x bar average or the mean, y value from the y bar, the mean, to get the sum of squares xy, which we already have from when we calculated out the things we need to do beta 1, same as our sum of squares for our x term. It's the sum of x minus x bar squared. So the only real difference is now we have our sum of squares y. So it takes the squares the difference in our y from the average y value, and we take the square root of that, and that gives us something called Pearson's R, or coefficient of correlation, and it ranges from -1 to +1. So if something is positively correlated, it will have an upward facing slope. So the data will kind of look like it's going up, and then you can tell that it's positive. So y increases as x increases. If there is no correlation, then it will look kind of like a blob on the scatter plot. So our correlation will be 0, so we'll have a 0 sloping line, and this just looks kind of like randomly generated uncorrelated data. So there are little or no relationship between y and x. And if it is downward facing slope, it is negatively correlated. So y decreases as x increases. So as correlation only ranges from -1 to 1, the closer to these extremes, the more of the data points will fall on our regression line. So if r equals 1, that's a perfect positive relationship between y and x. So all of our dots in our scatter plot will fall on the same line. And likewise, if r is equal to -1, it's a perfect negative relationship between y and x. All of our points will fall on the regression line. It'll just be negative. Finally, if it looks something like this, it is either not correlated or at all, or it is correlated but not linearly. So this looks more like a quadratic function, like a hyperbola, just upside down. So we're not going to get into nonlinear regression, don't worry. Okay, so the coefficient of determination, probably more important than r, is r squared. It represents the proportion of the total sample variance around y that is explained by the linear relationship between y and x. Basically, this tells us how good is our model. The closer to 1, the better the model, or the more variance that is explained. And r squared can only be between 0 and 1. The best models are close to 1, and the bad models are close to 0. So, going back to our example, you were marking analysts for Hasbro toys. Let's calculate and interpret the r squared. Fortunately, Excel calculates it out. We get an r squared of 0.81, which is pretty good for such a small data set. We're going to talk about multiple regression in a little bit of time, but the major difference, the only time you can really interpret r squared here is for simple linear regression, which is just one x value. Once we start adding x values, we have to switch to the adjusted r squared. So the output here, it's a little different than what we get in Excel, but here's our r squared value. Like I said, the adjusted is going to account for the number of explanatory variables and sample size. So basically, this one is the only time we can use just flat r square is if we only have one x variable. That's the end.